In this video, we'll look at the notes for 2.3, the section which is called Well-Posed Problems. It starts by asking a question. We've set up Cauchy problems, we've set up and solved Cauchy problems for the heat equation and the wave equation, but can we set up a Cauchy problem for Laplace's equation? That is, the second partial with respect to x plus the second partial with respect to y equals 0. Is it possible to set up a Cauchy problem for this equation? A Cauchy problem is what we call a pure initial value problem. Pure in the sense that it has no boundary conditions, purely initial values. And Laplace's equation is static. That means it doesn't depend on time. So it seems that a Cauchy problem is not really appropriate for Laplace's equation. However, we can try to make sense of the question. Let's try to pose a Cauchy problem by replacing t with y. So we have Laplace's equation and what we're replacing our initial conditions with. So here we're looking at what are essentially initial conditions if you treat y as being our time-like variable, even though it's a spatial variable. So we have a starting y value of 0, and so we start with an initial condition of y at x comma 0 is some function of x, and now instead of the time derivative, we're looking at the partial derivative with respect to y at x comma 0, and we're assigning that to some prescribed function g. So we've set up what looks like a Cauchy problem, replacing t with y. So can we solve this? This problem that we've set up has certain difficulties, and let's look at a couple of remarks to try and make those difficulties apparent. So let's suppose that we start with what we're calling here remark 1. We start with f and g being equal to the 0 functions, constantly 0 for all x. Then you can see just from inspection that a solution to this differential equation, this initial value problem, as it were, is just the 0 function. So if you let u be equal to 0 for all x and y, that will be a solution to this problem that we have here when f is equal to 0 and g is equal to 0. Okay, so if you start with functions which are 0, the solution is the 0 function. Okay, so that's fine. But let's suppose that we perturb this just a little bit. So as you can see, we're going to let g be the same, 0, the 0 function, but we're going to perturb f just a little bit. And when I say perturb it just a little bit, what I'm looking at here, or what we're looking at here, is 1 over n times cosine of nx. So if n is very large, then this function is very small. So if n is greater than 100, for example, then the value of f at x is always going to be quite small because cosine is bounded between -1 and 1. So f of x is, in absolute value, is always less than or equal to 1 over n in this case. So if n is quite large, then this is a very small value. So we have a small bound on f at x. So that means that it's not that far away from 0. So that's what I mean when I say that we're just perturbing f a little bit. We're just making it so it's not 0, but it's close to 0. So you can find a solution to this problem, and the solution is given here. U is equal to 1 over n times cosine of nx times the hyperbolic cosine ny. So if n is large, then we see that this boundary condition has changed by a very small amount. However, the solution has changed by a great deal. For remark 1, we have that the solution is always 0 for all y. But for 2, we have that u at 0 y, 0 comma y, this is when x is equal to 0. So if we get rid of that x equals 0 term, then if we just let x be equal to 0, then we have cosine of 0, which is 1. So that just leaves us with 1 over n times, this should be the hyperbolic cosine. Let me just rewrite that. Let me just try a little harder to rewrite that. So we're letting x be equal to 0, So that cosine of 0 is then 1. But then we have what's left over is 1 over n times hyperbolic cosine of ny. Now this term goes to infinity as y goes to infinity. That's because this hyperbolic cosine is a linear combination of exponentials. So it's a linear combination of exponentials which grows as y goes to infinity. So what we have here is a solution based on initial information which is not that different from in case 1. So in case 1 we started with f was 0 and g was 0 and we got that our solution was 0. But in this case 2 we start with g equals 0 and then we just perturb f a little bit so it's very slightly different. But our solution ends up being very different than 0. We end up with a function u which as y goes to infinity you can get the solution exploding, blowing up. So this is problematic because in physical problems, we want small perturbations in the boundary conditions to result in at most small changes in the solution. Because after all, if you're just measuring something without perfect accuracy, you want an approximation to be sufficient to come up with a reasonable solution. Here, we can imagine that our initial information is very close to 0, but not actually equal to 0. Or maybe we've estimated it as being 0, and we get a solution which is 0, but this is quite different from reality. So this is problematic that we start with slight perturbations in the boundary conditions, but end up with very, very different solutions. Let's just go to the next page here. So this just says what I just said out loud. In particular, if our boundary conditions are based on approximations, we want our solutions to be approximately correct. So this property is known as stability. The Cauchy problem for Laplace's equation does not display stability. It is not surprising that the Cauchy problem for Laplace's equation does not lead to stability because Laplace's equation models steady heat flow. So we expect that we need to satisfy some sort of temperature along the boundary or the flux along the boundary. If you specify the temperature along the boundary, that gives us what is known as a Dirichlet condition. If you specify the flux along the boundary, that's going to give you a Neumann condition. We expect to need one or the other, but in our attempt at posing a Cauchy problem for Laplace's equation, we actually tried to impose both of those. We say that the Cauchy problem for Laplace's equation is ill-posed, which is just another way of saying it's not well-posed. Well-posed is a technical term. It actually has a definition. We say that a problem is well-posed if the following conditions are satisfied. 1. The problem has a solution, that is, there is existence. 2. The solution is unique, which we call uniqueness. And 3 is exactly the stability issue that we've been talking about. Small changes in the initial conditions or boundary values leads to small changes in the solution. And as I said, we call that stability. For 3, we say that the solution depends continuously on the initial or boundary data. If 3 is satisfied, that is, we say that the solution depends continuously on the initial or boundary data. Let's look at an example. In this example, we have two Cauchy problems for the heat equation. Notice that these are the heat equation here, both of them. The difference here is we're going to specify different initial conditions. So for the first problem, which we're calling 1 here, we're specifying that u at x comma 0 is equal to some function phi. And in 2, we're specifying that v at x comma 0 is equal to psi at x. So in other words, we're giving different initial conditions. Now what we want to assume is that phi and psi are close in some sense. One is perhaps a slight perturbation of the other. We want to assume that phi and psi are continuous bounded functions, and we want to make sense of what we mean by close. So we want the two functions to be close in some sense. So we can make that precise by saying that their difference is bounded. So this is what we mean by the functions being close. If you look at the difference between phi of x and psi of x, that difference in size will always be less than or equal to some positive number epsilon. Epsilon is going to be some small number, but it's some tiny number that's positive. And however, the smaller that epsilon is, the closer these two functions are together. So that's what we mean when we say that they're close. That means their difference is never large. They're always close to one another. So we're going to assume that phi and psi satisfy this relationship. So the absolute value of phi of x minus psi of x is less than or equal to epsilon for all x. Okay, so if u is a solution to 1 and v is a solution to 2, then we actually know how to write down the solution because we've solved Cauchy's problem for the heat equation. So for equation 1, we have that u is given by this function, u at x comma y is equal to this integral from minus infinity to infinity of phi at y times g at x minus y comma t dy. Remember that g is the Green's function for the problem, or the fundamental solution, or the heat kernel, however you want to call it. And for 2, we have exactly the same thing for v, except we just replace this phi with psi. Now, if you measure the difference between these two, u minus v, then that is less than or equal to the integral from minus infinity to infinity of the difference between phi of y and, this should actually not be phi of x, this should be psi of y. I don't know why I made that mistake writing up these notes, because we're just doing the first one, and then from that we're subtracting the second one. So we're just looking at the difference between phi and psi there. So that should be phi of y minus psi of y, as you see there. So this difference between u and v is bounded by this doubly improper integral, where the integrand is given by the difference between phi and psi at y times the size of this heat kernel. Now, this difference here between phi and psi, we know that that's always less than or equal to epsilon. So this thing is always less than or equal to epsilon here. And that just leaves us with epsilon times this integral. But this integral, you might remember that g was a probability density function. So the area underneath the curve is 1. First of all, this is a positive function. It's an exponential function, so it's definitely non-negative. In fact, it's positive, and so this thing, the absolute value is just equal to g, and the area underneath that curve is equal to 1, so you just end up with epsilon. So in other words, if you start with boundary conditions, or initial conditions in this case, where phi and psi are close to one another, then their solutions are also close. And they're close in the same sense. So that is, if phi and psi are within epsilon of one another, then it's also true that u and v are within epsilon of one another. So if the initial conditions are close, then the solutions are close in the same sense. What this means is that this is a well-posed problem. We have a solution, we have a unique solution, and we also have stability. Stability is exactly this idea that if you have slight perturbations in the initial conditions, you only end up with slight variation in the solution.